So next week, Monday, we have our first exam, right? The exam, the content of the exam would be homework 1, homework 2, all the CPs, today's lecture. But today's lecture, you'll see that at some point you need to use computer to solve the problem. That's not part of the exam, but knowing the formula is. All right. Those of you that had class with me, you know that I allow cheat sheet, but you can only bring equations. You cannot bring solved examples. And I will check all the cheat sheets when I grade. And the idea is, since you're bringing all the equation, putting the equation in your question does not get you any credit or points because you brought them in, right? So you expected to know how to use them. So if you see a question and then say, I have no idea how to solve it, but you might have an idea, you don't know how to write it, but you can explain in English that I think I should do this and that, but my brain is freezing right now. You get some point if your thought process is correct, all right? You cannot bring calculator for this exam 1 only. The question will be straightforward enough that you will not need calculator, all right? So more on concept and those kind. On Friday, I already posted sample questions. I'm going to talk about those. I usually have exam review before exam, but I'm not going to review the slides, the lectures. I'm going to tell you what kind of question you can get. And then I will bring examples of the problems. So it will be something like that with a different problem. But so best policy is before coming to the class on Friday, take a look at those questions. All right. So you at least be ready to hear what I have to say. Then I know everybody will just study on the weekend. So I don't think anybody will study from that. All right. Sounds good. Okay. Office hours is still, nobody shows, it's okay. I'm just checking if you need extra office hours, you need to email me. Otherwise, I'm assuming everybody's cool with that. Okay. All right, last class, last week, well, Friday was our industry day. I hope you found it useful to see that what we learn in theory actually has application in industry. If you're interested in robotic, it would be what the example they brought was simple examples, but still you could see how related it is to what we were learning here. On Wednesday, we talked about forward kinematic. I introduced you the PoE method. You had a couple of examples and you solved CP9. Now, for all of you that you have the book, it's one of the solved examples of the book. If you don't, it's free. You have the link. It's good to look at the solved examples of the book. It's just extra practice problems for you. Today, we are going to finish basically the PoE method. The last part is Rodrigues formula, how to do those e to the power of bracket s theta, how to solve them. All right, once we have that piece of information, then you're good. You know how to solve for forward kinematic. All right, so Rodrigues formula says that for a vector omega theta, that's part of R3, theta is any scalar value, and your omega is a unit vector. We can write the matrix exponential of omega theta into a rotation matrix. So you remember that e to the power of s bracket theta was equal to rotation of omega of theta, right? And s bracket was composed of skew symmetric of omega and theta. If you forgot, go back to the lecture that we talked about on Wednesday. Now, how to find that relationship? So e to the power of bracket omega theta is equal to that rotation, which you can expand it as such. I, which is your identity matrix, plus sine of theta. If your theta is in degrees, it's sine is in degrees. If you have in radians, it's in radians. The sine of theta is going to be a scalar number. So it doesn't matter. You just have to pay attention to what are you doing. Then skew symmetric of your omega. Now, if your omega is a 3/1, what is skew symmetric? What's the dimension of a skew symmetric of omega? 3/3, right? So then what is the dimension of your identity matrix I? 3 by 3, we're able to do the addition. So 3 by 3 plus some number multiplied by 3 by 3 matrix plus 1 minus cosine of the same theta against the number, so it's scalar, and symmetric of omega to the power of 2, again 3 by 3 matrix, right? So this will give you a 3 by 3 matrix, which you expected to be a rotation in a 3 by 3 process, right? So this is how you would expand. So that's the last piece of puzzle. If you remember, right before our kinematic expression, we said T of theta, the transformation, is equal to e to the power of bracket S1 theta 1 multiplied by e to the power of bracket S2 theta 2 dot 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 times M, which M was what? The home position, right? The home position is 3 by 3 matrix. Well, 4 by 4 matrix, composed of a 3 by 3 and a 3 by 1 and zeros and 1, right? Now, if we can fix this part of the equation, then we can find a transformation for them. Every time we have a 3 by 3 and we want to be able to fix the dimension, we just do the appendix. Like we just add 0, 0 if it was a vector and 1 if it was a point, right? Now, Rodrigues formula can be used in anywhere, anytime you have a rotation, a vector that you're rotating around. So forward kinematic is one of the applications of it. You're using it to solve a forward kinematic problem. But the example I brought to just show you, let's say that you have a frame S, right? And you are rotating it about a unit vector. So it's none of the principal axis. It's just a vector, unit vector for 30 degrees. So your unit vector still has component in X, Y, Z direction, right? So let's say frame B is rotated from an initial orientation aligned with frame S about a unit axis omega 1, which omega 1 is 0.5 and 0.866. So omega 1, omega 2, omega 3, right? Transpose. And we are rotating it by 30 degrees. So axis angle rotation. Now we want to know if we do this rotation, what would be our rotation matrix? Remember, axis angle rotation was one of the ways that you could represent the rotation. So let's say I have the axis, I have the angle. How do I write the rotation matrix? You put, so this would be your omega, and that's your theta. You create this sentence, and then your solution will give you the rotation. Right? So do you want to solve that with me? So we're trying to find rotation of omega 1 and 30 degrees. So it's going to be an identity matrix plus sine of 30 degrees skew symmetric of omega 1 plus 1 minus cosine of 30 degree skew symmetric of omega 1 squared. Something that you want to bring to your cheat sheet, put added to your cheat sheet, is if your omega is omega 1, omega 2, omega 3, then your skew symmetric is going to look like this. 0, negative omega 3, omega 3, 0, omega 2, negative omega 2, negative omega 1, omega 1, 0. So I is 1, 0, 0, 0, 1, 0, 0, 0, 1, plus 1/2, 0, negative 866.5, 866. Where do I bring these numbers? Did I bring them here? I use those as omega 1, omega 2, omega 3, and then plug them in that so I can create the skew symmetric. Plus, this is going to be 1 minus point negative 866. I'm gonna bring this whole thing a bit lower. 2. Then if you solve this rotation about omega 1 for 30 degrees will give you a rotation matrix that looks like this. What happened? Oh, yeah, there is this guy because there has to be negative 1.5. Thank you. Hopefully this final solution is correct because it's from the book. All right, some 3 by 3 matrix, which is the solution of that. Now, obviously, this is something that in your coding programming, right? You can include that. And once you have your omega, the code will run and give you the rotation matrix for it. So chances that I'll give you calculation of that in the exam are very low because it just takes time. Right, or 55 minutes, but you need to know the equation. Yes, you need to know. So what each elements are, for example. All right. Yes.
Did you ever specify that we need to use that?
So thank you. Very good question. So when I give you PA, so your PA is our PH2 is already up. I don't know if you can see it or not yet, but I want to specify which method to use. You will decide Euler angle, row pitch yaw, or this one, right? At the end of the day, since you will have, like you'll see that if you read it, you will have an animation or simulation. The most you end up in the same orientation and position if you use any of those methods. So no one will force you to use any of the methods unless they're checking, for example, if I want to check if you understood Euler method, right? Otherwise, you're free to use any of them. You might think that, oh, this is like really complicated, that big matrix, but in reality, a lot of times you actually have to use it. Because remember, you close your eyes and moved around, like you had my final position. So finding one axis and one angle would be easier to guessing what direction you actually could. You could find that, good. If not, this is a good method.
So say for examiner things, looking at equation, obviously, but I guess expected to be able to understand how the input value, like have the whole expression.
Yeah.
But just not.
Do it. Yes. So just like what I did here, for example, for exam, you would stop, not have this work, because in real life, in reality, I would actually fulfill that. So I'm not going to put it in that. But the ability to develop that expression is something I would expect you to know how to do it. And then, so this is your final, so this would be the rotation matrix for this guy if your original frame rotated about that unit axis for 30 degrees. Now, so we learned how to use Rodrigues formula to find e to the power of omega theta, and it gives us a 3 by 3 matrix. But we know that for matrix exponential, we would need a 4 by 4, right? So there's a little bit more than just appending it with 0 and 1. So e to the power of s theta, that's what shows up in your forward kinematic, will be comprised of these 4 elements. So they look familiar, right? Just what you saw. So this is the rotation part of it, right? And then this is 0. This is what the position will end up being, and this is 1. So this is a vector. This is the position. So that's appended by 1. So in your forward kinematic, if you have rotation only, this is the expression you will use to expand or write your e to the power of s theta. If you don't have rotation, but you have v as your velocity, what are you having? What is the type of joint? prismatic, right? You don't have to go through that. You can directly use, it's pretty simple because this would be zero rotation, so it's identity matrix. 0, 1, you just have the region velocity. And theta here, so we are going to use theta as a joint variable. Now, if your joint was a revolute joint, theta is representing angle. If your joint was a prismatic joint, what does theta represent? Position. We're just calling it theta. You can say theta equal to d because it's easier to say d for distance. Do that. But as a general closed form expression, we just use theta as a placeholder for joint value. All right? Does that make sense? And we have two cases. So if you have prismatic joints, you just directly look here. You don't have to go as well. Yes.
So whenever we have like the S matrix,
Mm-hmm.
that will have the 0 in the bottom right hand corner, right?
You have what?
It'll have a 0 in the bottom right hand corner, that's in its velocity. So once you multiply that by theta, that turns to 1. It's that.
So these are 0 because this is all rotation.
Yeah,
Yes. Yeah, these are vectors.
yes, but like, so in like the S matrix itself.
Also has 0,
It
0.
has 0, 0, 0, because velocity is fraction.
Yeah.
Okay,
So
so remember we multiply by theta, we have to add that 1 because theta times the velocity.
yes.
Okay.
Yes. I got confused a little, but yes, you're right. Yes. But in short, trust the awesomeness, follow the equation, it will give you the solution. All right. But yes, every time you're checking, your vectors have to have 0 to be appended to be 4 by 1. So this is just to fix our 3 by 0, 4 by 3 to 4 by 4. These two do nothing. And you're multiplying, they just make sure that the multiplication will end up to a correct form. All right. And where those omega and v come from? You remember that S had omega rotation and v as velocity, like which could be because of your prismatic or induced by rotation, like the linear velocity action. So those are v's and omegas. So this is if only prismatic. And you can say theta is a placeholder for joint variable. So theta is angle, then you have rotation. Theta is distance, then you have prismatic. I usually try to show prismatic by D, just make it simple. But again, if you're looking at an example in literature, a question that gives you theta for prismatic, it should not be shocked that, okay, what is it? It's just a variable, just name. All right. So this was an example of Wednesday that I said you should do by yourself, right? When you study. How many of you study? 0. Great, 1. We're going to do. The thing is, we don't have enough time every class for me to solve many examples. So I will just give you, it would be good if you try to think about this. And the solutions are in that annotated version, but reading from the solution will not help you to learn. You actually have to challenge yourself to do it. Fail, then look at the solution and say, oh, okay, that's what it is, and then you will remember. All right. There's another example of that kind at the end of this lecture, which is up to you if you want to do it. All right. So this question is from last class, is asking about home position M and screw axis SI. So those brackets, those vectors, right? 6 by 1. So we're going to try to find that. Now, every time you have an example like this, you're going to identify your base frame, fixed frame, frame S, frame 0, and also identify your end effector frame. Why? Why do we care about end effector? Yes, you define matrix M for the end effector, right? But if you remember, we said that for forward kinematic, you want to know the orientation and position of your end effector at different angles of the robot joints, right? That's why you want to identify where our end effector is, because you're solving for the end effector. So this is going to be my base frame. This is end effector frame. We can show by EE end effector. So it's frame B. If you did not have, it's very important, please listen up. If you didn't have distances, for example, on the first 3 joints, so let me show the joints. I'm going to show the z-axis. Hopefully you all agree that this is z in that direction, z2, and this is z3, right? So I can say theta 1, theta 2. I could say theta 3 or d3, whichever you like. I'm just going to call it theta 3 now. You see that there are no distances are given for that on this model. This is the model of the robot. What does it tell you?
Your body frame is still that. First 2 aren't really.
Think of more physical, like physical robot. So this is a model someone took from the actual robot, right? When we look at this model, what does it tell us about the actual robot? You should be able to go both ways. There are coins, right? There are one joint. So the 2 rotation, like the example in your homework, and then they also move together along an axis. So if you don't have distances, you can assume they coincide. So all of their frames can be in one frame, right? If you had doubt, you can write. Joint 1, 2, 3 are assumed to be coincident. It's all good, right? I usually actually write that. So for example, here I would say first 3 joints coincide. So in engineering, we usually make a lot of assumptions. As long as you introduce them, you're good. It has to be close to the reality. Now, if someone say, no, actually, you know what, there is a distance A from here to there, like, okay, it's a simple fix in your equation. Right? It's not a big deal. You don't have to redo everything again. All right, now knowing that, let's write your M, the position of the end effector. So this is end effector ZB in the direction of ZS, XB in the direction of XS, and YB in the direction of YS. So that's an identity matrix, it didn't rotate, right? So 1, 0, 0, 0, 1, 0, 0, 0, 1. And since these are vectors, we put 0 at the end to fix that. Now, for the position, we want to know the origin of the end effector, frame B, is positioned with respect to frame S, or from the perspective of frame S. You'll see that in X direction, there is no translation. So I'm going to put 0 here. In Y direction, in the positive direction of Y, we went L1 plus L2. So the positive direction matters. L1 plus L2. And in Z direction is 0. So this is your M position. Now, both of those frames are arbitrary chosen, right? So now if someone chose the direction of X and Y and Z in any other direction, it doesn't matter. You would create an M that matches that. Does that make sense? If you had the directions of your axes, easy, you just write it. If not, you assume a direction and say, here's how I'm solving it. And you write your M that matches that. Right? Now, what's next? So I created M. What's next? So we're going to create that table, right, to help us to find omega I and VI for every joint. So we have, let me continue finishing. So this is theta 3, theta 4, theta 5, theta 6. I'm gonna write this in blue, so it's blue, okay. And then you see that there is no direction for z-axis, but I know the rotation and translation always happen in the direction of positive z. So you can basically find for theta 4, the direction is toward here. So this is your z4, z5, and then z6, that direction. Now, if someone gave you the direction of z, you will use the same method to find the rotation, the direction of rotation. Always positive direction. Now we will create our table. I have 6 joints, so I is 1, 2, 3, 4, 5, 6. Omega I, QI, then VI. You can bring cross product equations with you. Totally okay, because you need to use it here. So omega I, Z1 in the direction of ZS, the other two are 0, so 0, 0, 1. There's no QI because they coincide. So actually for the first 3, so VI, we know it will be 0 because it's not offset. So if they coincide, there's no offset, so there's no VI from it. Z2 is this one, it's in the direction of X. So it's 1, 0, 0. Again, my ones and my commas look the same, so feel free to ask what is what. So join 3. What's omega 3? 0, right? Because the prismatic joint. So that's basically the only like point that this question had. So 0, 0, 0. So Q doesn't matter, right? We don't even need to find it. I'm gonna put a line because omega cross product, like anything will be 0, so it doesn't really matter. And then VI. So what's the direction of translation of theta 3 as seen in S frame? 0, 1, 0, because in the Y direction, 0, 1, 0, because it's in this direction and that's the positive direction of Y of S. So that's the only difference this question has from your CP9. CP9, there are all rotary joints. This one has prismatic. So if you had 3, 4 prismatic, 2 rotary, you should still be able to solve it. There's no big difference. Actually, prismatic is easier. You don't have to do the cross product thing. So 0, I'm just writing for the rest of them. 0, L1, 0. This is again an example of your book. So I've done this, but I'm trusting the numbers from the book as well. L1, 0, 0, 0, negative L1. And the last one is 0, 1, 0, 0, L1 plus L2, 0, and then 0, 0. So that is our table. Now, the question asked us about the screw axes. So S1 is going to be, we pull out 0, 0, 1, which is, I'm going to use different color, this guy, and then 0, 0, 0, which is this guy. So that's how you create all of them. S2. Now, here's the point. If I give you any screw axes that look like this, and I ask you about what kind of joint this is, you should be able to identify, right? 100%. These are zeros, so this must be a prismatic joint. We even know what direction. So we went from an actual robot to a model to mathematics. So you do not need to know the model anymore. This can be now translated to computer code. So every single time you deal with robotic model, mathematics, and you should be able to go from mathematics to model to the actual robot. All right. Ah, no, that's wrong. See, don't be me. Don't make this mistake at your exam. There, you would have lost some points there. All right, so that's the end of it. If I didn't ask for the kinematic expression, you stop here. If I ask for kinematic expression, you write theta is equal to t theta equal e to the power of bracket s theta 1, and then you create what bracket s is, right? And then that's the expression. If I ask you to use the Rodrigues formula and expand those s, you already know how to do that. So you get 4x4 matrices, but that's at the end of it. Then you code to solve. All right. This is one of your book examples. This is an actual robot. So this universal robot has 6 joints. You have all the distances between the joints. So L1, omega 1, W1, W2. Your frame S identified is here. So these joints are on top of each other. Then you have your frame B or your end effector at the end of this joint. Then from this, you can go to model, you can draw something that is simpler for you, or you can just use this to create the table for omega I and EI. All right. So read the question, try to see if you can write M composition and create that table for all the joints, those 6 joints. I'll give you a little bit of time, then I'll solve it.